Hey there. So we're going to go over Notebook 7, single variable visualization. So if you want to go ahead and get Notebook 7 open, and we're going to start off talking about categorical variables and the types of visualizations that work best for them. So we're going to start off with a quick review of dot width column, and we're going to add a column to the top movies table. And we're going to use dot where like we often do to specify two columns that we're going to want to look at. And we're going to remind ourselves of both how to use dot take. Remember, dot take selects certain rows, but the input into dot take, sometimes I need an array. This is going to get the first 10 rows in the table, and then I can make a bar H of the top 10. And if I use sort with descending equals true, then it will sort it from the top down, so it'll be the best at the top. And when I do this, we do this a lot with the dot group dot sort and then bar H, and of course the descending equals true on the dot sort. And that's called a Pareto graph. So we're going to start off taking a look at all of that. Let's click over here. This is Notebook 7. And the first thing is we are going to look at some bar charts. The table that we read in is called Top Movies. And so we have the title of the movie, the studio that produced it, and here they focused on Disney movies. The gross, now gross adjusted is going to be adjusted for inflation. So some of these movies are very old. And so Snow White and the Seven Dwarfs has a much higher adjusted gross. Why? Well, because there's been a lot of inflation since 1937. Okay. So here is our top movie. All right. And then what are we doing? Well, we're creating a column that's going to be called millions. How do I know that? Well, it's with columns. So the first thing in is the title of the column. And then the next thing we need was what goes in it. And we are dividing by 1 million. Why? Because the gross divided by 1 million, that's going to give me the number of millions. So if the movie grossed $8 million, now it's going to be 8.0. And if it grossed $9.5 million, I'm going to get 9.5. So I'm going to see the number in millions, and we'll see how that goes. And notice that we use the dot take NPA range 10. So what is NPA range 10 going to do? Well, it's going to take rows 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's going to stop at 9. Remember, it always stops, NPA range always stops one item before the stopping criteria. And then we're doing bar H, so we're doing title and millions. So you can see the top 10 in the table. But why don't we sort based on millions? Descending equals true, and so this will be the top 10. This will show the top 10 in descending order. And this type of bar chart in descending order from most popular to less popular is called a Pareto bar graph, okay? And we do this a lot, again, with a dot sort and then dot bar H. Okay. So now if we just use a dot select studio, we're only getting a column of just the studio. And notice that there are some doubled up names, right? So now we're going to switch to a dot group based on studio, and you can see how many movies each of these studios produced, at least that are in the table. Okay. And now what's this going to do? This is going to pull out the count, right? The numbers in this table, and it's going to sum them all up. And yes, there are 200 movies in the database, so this makes sense if I sum up the count, right? Dot column pulls out the array of numbers so I can do some math with it. And dot sum is the function I decide to use. So there are 200 movies. And here again is the dot bar H, and you can see it's kind of a mess. And if we want, we can sort it with descending equals true, and this puts the movie studios that have produced the most movies in this database near the top. So Buena Vista and Warner Brothers were the top two. And again, this is called Pareto. All right. Okay, so now we're going to talk about a classic visualization, the histogram. And Python has a really nice feature where we can do group equals, and we can produce two histograms overlaid on top of each other for different groups. Say, for example, biological sex, males versus females or something, could be our grouping, or freshmen, sophomore, juniors, seniors, depending on what the grouping variable is. Also, we're going to talk about binning. The sad thing is that a lot of machine-generated histograms don't look all that great, and we have to change the bins, which is the intervals across the x-axis, to make the histogram useful. Okay, so it's not that it's bad, it's just that the standard one sometimes doesn't work as well as we would like. So we're going to use the Galton table. Oh, I'm sorry, this is the baby table. And let's take a look at what we have here, right? So birth weight, this is in grams, the birth weight of the babies, gestational days, maternal age. These are pretty self-explanatory. Maternal height, maternal pregnancy weight. And then I want to say maternal smoker, this is an old data set. Why do I mention that? Well, we have some modern sensibilities about no, during pregnancy, probably shouldn't smoke, and some people even give up caffeine. So the modern approach to pregnancy is much more health conscious. This is an older data set, and it's not that the people weren't health conscious then. It's just that things weren't as known. There weren't as many recommendations from doctors and health organizations. So, and the very first thing we're going to see is they're taking this birth weight. Why would they look at birth weight in this particular histogram? Well, back then, birth weight was considered a measure of how healthy the baby was, and healthy babies would weigh more, which is true. I mean, to an extent, it's not a perfect measure. And you can see when they group this based on whether or not the mom had smoked during the pregnancy, right? The smoker equals true is gold, and the smoker equals false is dark blue. And you can see that it appears that the dark blue bars are just a little bit to the right. The babies are weighing just a little bit more. And like I said, in that day and age, that would be considered a sign of healthier babies in general. Okay, now look at the counts. And this is where I want to caution you, right? There were, in this data set, a lot of yes to smoker, yes or no, right? And that's probably not the case today. But again, it's an older data set, and there was just a different culture around the health of the mom and the baby during pregnancy. So, yeah, there's probably a lot more smokers than there would be today. Okay, so now we're switching to the top movies, and we're adding this column age. And what is age as well? We're taking, and I switched this to 2023 minus the top movie.column.year. So if the movie was made in 2003, then it's going to take 2023 and subtract 2003 and say, hey, the movie's 20 years old. Okay, so then we're adding that column using a with underscore column. We're adding the age of the movie. Okay, so Gone with the Wind is 84 years old. Okay, and there are some younger movies. And so we want to talk about binning. All right. Why? Well, again, we're trying to display the result better, and machines are just notoriously bad at creating good histograms from scratch. And so here we go. They're looking at the ages of these movies between 6 and 102 years old, right? And so they're creating bins. So the array is just using the tens, 0, 10, 20, 30, 40. And notice that the minimum 0 is below the minimum age of 6, and the maximum of 110 is above the age of 102. So these bins should cover. All right. And here we're showing the bins. Okay. And you can see how many movies fit in each of these bins. All right, and notice that we're still summing to 200. Again, this is a check to make sure that we've got it working correctly. And since it's working properly, it's showing 200 as the sum. Okay. And here is a slightly different set of bins. And yet another set of bins. Okay. And also, they're just reminding you of the dot where all the movies where the age is 53. Okay, Love Story, Airport, MASH. That's kind of funny. I'm sorry, I'll just let you know. This may or may not be my age, but yes, MASH did come out the year I was born. Okay. So here are my bins and the bin data. Okay, and now we get to make our first histogram. Okay, and we're just letting the computer do it. And like I said, it turns out that this is not a particularly good picture, right? I mean, we can kind of see what's going on, but perhaps there's more to the narrative here. So if we use our own bins and we're using NPA range from 0 to 100, counting by tens, and again, this will stop at 90, right? It won't count all the way up until the last year. Boom. And it turns out, do you see the difference, right? So here we kind of just have the ski jump. It's pretty much just straight down. And for better or worse, when we change the bins, we can see that there is a little bit to the left side, right? So this is starting to show evidence of a bell shape, right? But these smaller bars over here were not even present in the other one. And that's, again, why do we do binning? Why do we change the bins? Sometimes there's more to the histogram picture than we're seeing, okay? And that's what that's supposed to show. So now we have density equals false. Notice that that the y-axis here is in percentages. Okay, but when we move down, the y-axis is in count, right? They actually count the number. This is 21 movies, or yeah, that's about 21 movies. This is 35 movies in these particular age ranges, right? And why is that? It's because of this density equals false. Okay. And then here we go, we're not trying to specify any bins at all. And we go back to the ugly old one. It's not ugly exactly. It just doesn't show the full picture. Okay, and now they're talking about how to calculate the height of the bin. Okay, so the first step is to calculate the percentage of movies that are in that bin. Okay. So this is going to go up to that bin data table and find the bin with 40 and see what percent of the movies are in there. And it turns out that's 13%. And then it's going to calculate the width of the interval. Well, that's just 66 minus 42, which happens to be 24. And then the area of the rectangle is going to be height times width. And it turns out this area is representing the percent So when I solve this equation here for height, I have to divide through by width. So I'm taking percent divided by width to get the height. So the height of the bar should be about 0.5416. Again, you'll notice that we were working in percents instead of counts. And what are the heights of the rest of the bins? They do the exact same thing. They get the left endpoint of all the bins, and they're going to get the width of all the bins. And then they're going to calculate the bin heights. How? They're taking the percentage based on the bin left and dividing by that bin width. All right. And you can see what they've done. They've created the result in this array, so you can see that. And we're showing, again, this is the good view of the histogram where we've created the bins that work well. Okay. And on a histogram, the bins should all be the same size. And we're looking at the survey data now, handedness, and they ask, I don't know, which pant leg you put on first, I guess, and sleep position. And they're showing an interesting histogram, right? And it turns out that these bins don't really show much. I mean, the histogram is not really telling a good story. There appear to be holes in the data and so forth. And here we go. This is again why we use bins, because this is a histogram of the same thing, but it shows more clearly what's actually going on with this data. So what we're going to talk about now is the box plot, and I want to make this point because a box plot is a picture of the 5-number summary. And it has 5 horizontal lines in the box plot. We'll have pictures of this in the notebook. The bottom is the minimum. The next line up is the 25th percentile, and we call it Q1, or the lower quartile. The 50th percentile, which we always think of as the median, it's true if you think about it, it is in fact the 50th percentile. The 75th percentile is Q3, and the maximum. Those are the 5 horizontal lines in a box plot. And there are some questions on quizzes and tests that will ask you about these numbers, Q1, Q3, and so forth. And we are going to show some interesting box plots. I will say that we don't have this quick group equals option for box plots. It would be really nice if the computer would just create side-by-side box plots for us, but it sadly does not. All right, so let's take a look. And here's the exact same thing that I just said, right? That the 5-number summary is going to be what's shown in the box plot. Okay. So here we have skyscrapers data. And notice that we have a table called NY, which is all of the skyscrapers in New York City. And we have an LA table for all the skyscrapers where the city name is Los Angeles. And the one we're showing is actually the New York skyscrapers data set. Okay. And notice we're just doing plots.boxplot. And then I'm putting an array in there. You see this? This is saying, hey, take the New York table and pull out column 3 as an array. Okay, so the New York table is right here, so we can see it. Sorry, right here. And this is the 0 column, the 1 column, the 2 column. Remember, the computer starts counting at 0, so height is actually item 3. It's the 4th column, but again, the computer starts counting at 0. Okay? And width equals 0.4. That's not all that necessary. Sometimes you can change the width because it displays better. So we put in, and this is exactly what we're seeing. So we've got the minimum. We've got Q1 or the 25th percentile. We have the median. We have Q3 or the 75th percentile, and we have the maximum. Now, you're going to say, hey, well, I see these outliers here, so that's obviously not the maximum right here. This is not the maximum. Okay. We do adjust the max and the min when we put things in that are called fences. And anything inside the fence is not considered an outlier, but if it's beyond the fence, it counts as an outlier. So the box plot is, in fact, not showing exactly the 5-number summary. But we have a special version that can show the box plots. Okay. And here we've just added a title. It's the same picture. And we do have the ability to display the mean. We put the show means equals true. And what it does is, if you see the gold triangle, it puts that at the mean. So the line that has a little bit of color to it in the middle there, that's the median. So in this case, the mean is above the median. Why is that? Well, remember, outliers are influential data points. And why are they called influential? Well, because they're pulling the mean up. And they don't have very much effect on the median. So when the mean is above the median, it's usually because there are outliers above, but there's none below, or very few below. All right, and when the mean is actually below the median, it's the outliers generally that are causing that. There will be outliers below, but not above. All right, so show means equals true can help me see the relationship between the mean and the median. Okay, now this is a slightly different width, so we've made a wider box plot. Show means equals true is still on. Okay, now we're going to do side-by-side box plots. Now, what do you need to do? Well, we have to get one group. We have to get its data as an array, right? That's why we're using dot column. So this is the New York City skyscrapers pulling out column 3 as an array. And then our second group is the LA skyscrapers. Again, column 3 is their heights. And then the other thing we're going to do is we're going to label the box plots so we can see which is which. Don't have to touch anything else. So your instructors have provided this code block for you. All we have to do is the part in here where we use the dot column and the right table to get the data as an array, get the numbers as an array. And then we change the titles. That's all we have to do. The rest of the code block we can leave alone. And sorry, back down to the skyscraper. And the interesting thing, at least to me, is that the medians are really close. Now, you may see one is slightly higher, one is slightly lower. But it's interesting that in New York City, they have a lot taller skyscrapers. And I had a thought question for my in-person class. Why is it that New York City seems to have more tall skyscrapers than LA does? And after a few seconds, they came up with the idea of earthquakes, right? If you have earthquakes, maybe it's a little harder to build a tall building that's going to withstand those earthquakes. And since they don't have that problem in New York City, they can build these taller buildings and still be safe. Okay, so I think it's a safety issue in LA. But you can see the difference in the box plots. Here is another pair of side-by-side box plots. This one has the show means equals true in it. And notice that even though the medians are very similar, there's only a couple of outliers. for LA. There's more outliers and they're more extreme outliers in New York. So the average height of New York skyscrapers looks to be taller. Not a bunch, but looks to be significantly taller than in LA. Okay, so now we're back to the babies. Sorry, to the babies. Okay, and notice that the non-smokers babies, they both have a higher, the non-smokers has a higher median and a higher average than the smokers. This is fairly significant. I mean, these are in grams, so we're talking about, 7 or 8 grams difference. But on average, in this day and age, they're saying that, hey, these non-smokers babies were generally healthier than the babies born to smokers. Okay. And here we go with the final thing we're going to take a look at. So we have this Galton table which investigates children's heights compared to parents' heights. And then I want you to see this. We can actually produce several histograms at once overlaid on top of each other. And that's what this example is going to get at. Okay, so here's the Galton table, and you can see how many people are in the family, or how many children are in the family. I don't know. The father's height, the mother's height, the mid-parent height, how many children there are. I guess that's a child number. So this particular child was the first, was the oldest, I guess. The gender of the child, and then the child's height. Okay. And so he was studying, what impact the height of the father and mother would have on the children. Okay. So there are 934 children in this. So each child is a row. Okay. And here we go. Here's the histogram of mid-parent height. And this makes sense. It's not quite the average of the heights, but it's close to the average of the mom and dad, mother and father. And here's the histogram of the child height. And then we can ask this question, what about the children with heights that are above 70 inches? Which, if I'm not mistaken, is 5'10". Well, you can see everybody that's taller than 5'10" is shown in yellow. Why? Well, because we do this left end. It's not that common. We don't do it that often in this course, but it is a nice feature. Okay. And then here's the histogram of the mid-parent height and the child height together. And this is really cool because now I can see where the mid-parent heights are compared to the child heights. And interestingly, it seems the parents are taller. Or there are some shorter kids that were born into families with taller parents. And then here's the one I wanted you to see. So now we are doing a histogram with 4 different columns of data. So we have dark blue, yellow, light blue, and green, and all are showing different patterns. And here is the same thing done with box plots. So we have some really nice graphics showing what we can do with these category and numeric variables in terms of visualization.